Okay.
See, you should just ask. Say, do you want to move?
Yeah, but it's not fair. People in the front should have to go to the back for a while. Make you sit in the back of the bus. Okay.
You guys like sitting up front.
All right, anyways, let's go through this. Do we need to do 71 still? Do we need to do 71? No? We're good with that one? Okay. But is it fair to say that we need to do 73, 77, 79? Do you agree with that? Erica, you're killing my recording. 73, 77, 79. Do we need to do those three? Okay, great. So let's pull the book out. I love you, girl. But you're killing my recording. I'm not restarting it. All right. Hey, I'm actually kind of happy that the sound didn't come through on that last lecture, seeing as how half of it was spent talking about my facial hair problems. Now you know. All right. So let's start with question number 73 in the book. I love you guys. It says, the fizz produced when an Alka-Seltzer tablet is dissolved in waters due to the reaction between sodium bicarbonate and citric acid, and they give me the balanced chemical equation. When I start these problems, this is the first thing I do. I don't even read the word problem. I just look for the chemical equation, and I write it down, and I double check that it's balanced. And in this particular case, it is. It's going to take me a little while here. These formulas are long. All right, and then I continue reading. It says, in a certain experiment, a gram of sodium bicarbonate. So underneath the formula for sodium bicarbonate, I'm going to write 1 gram. Is going to react with 1 gram of citric acid. So underneath the formula for citric acid, I write 1 gram. Part A is asking which is the limiting reactant. B is asking how many grams of carbon dioxide form. And then part C is asking how many grams of excess reactant remain after the limiting reactant is completely consumed. All right, so let's start with the limiting reactant. First thing I have to ask myself is, are these givens in a unit that I can work with? And the answer to that is no. It's a resounding no. The gram is not something that I'm interested in. What do I really want to do with these numbers? Change them to mole. All right, so how do I change these values to mole? You divide them by the molar mass of the formulas off the periodic table. Okay? All right, so what is the mass of sodium bicarbonate? Anyone calculate it? It's 84.01. And the way that you derive that number is you take the mass of sodium off the periodic table, the mass of hydrogen off the periodic table, plus the mass of carbon, plus 3 times the mass of oxygen. All right, so how many moles is that? So 1 divided by 84.01, I get 0.0119 moles. And I would do the same thing over here with citric acid. I calculate the molar mass of citric acid off the periodic table. It's 192.14, and I convert that value to mole. The mole is a unit I can work with. That should be, again, your first gut instinct. Anytime they give you a number, change it to mole, regardless of what the problem is. It could be a kinetics problem. It could be an equilibrium problem. Always change it to mole, because in chemistry, that's the language that we speak in. We speak in the language of moles. All right, so to figure out who the limiting reactant is, what I taught you to do was that first you have to figure out what the theoretical mole ratio should be. And this comes from the coefficients in the chemical equation. So according to the equation, right, and I'm going to put these in the order that I see them in the equation as I read it from left to right. So according to the equation, you need 3 moles of NaHCO3. This is what my recipe calls for. To combine with 1 mole of citric acid. Those are the proportions that you normally need for this reaction to occur, right? What is 3 over 1 reduced to? 3, right? To make that much carbon dioxide, that much water, and that much sodium citrate. And I'm going to take this value and I'm going to compare it to what I have actually been given. Was I really given 3 to 1, or was I given a slightly different proportion? So these are amounts that you actually found on the shelf. All right? So you want to see if the amounts that were actually on the shelf in your stock room are in that ratio or not. So we're going to calculate what we call an empirical mole ratio based on the given amounts. And again, you're going to the key is that we're going to take the 0.0119 moles of sodium bicarbonate. You want to be sure that whatever substance you put in the numerator of the theoretical is the same substance that you put in the numerator of the empirical. All right? That's how much I was actually given of the sodium bicarbonate. I'm going to divide it by 0.00520 moles of the citric acid. And now I'm going to reduce that. 0.0119 divided by 0.00520. That happens to be 2.29. Okay, what happens at this point is that you have to evaluate that, compare that to your theoretical mole ratio, and try to figure out, is the substance in the numerator the problem, or is the substance in the denominator the problem? Which of these two things is limiting me? All right, so this ratio falls short of what you need, right? This is smaller than that value. This is what you want. This is what you've got. What does that tell you? If the empirical mole ratio is less than the theoretical, your numerator is at fault. Your numerator is what's making that number be too small, right? So that tells you that your numerator, this thing here, is your limiting reactant. So again, if your theoretical is greater than the empirical, your numerator is the limiting reactant. That's just a real simple way of figuring out who's limiting. At this point, usually, I go ahead and I label the limiting reactant on my equation with a big LR. And then I go ahead and identify the excess reactant. So where do we normally find reactants in the chemical equation? On the left or on the right of the arrow? On the left. Okay, so what's my excess reactant? Identify it. It's the other stuff. What does it mean to be an excess reactant? At the end of the reaction, will I have some of this stuff left over? Absolutely. Will I have any limiting reactant left over? No, not at all, because I'm going to use that up completely. All right? Okay, that's part A. Part B. They want me to calculate grams of CO2. So once you identify who the limiting reactant is, every calculation from that point on has to start with the value for that substance that you were given. All right? Am I going to go back to the 1 gram? No. I already did this step. Let's go ahead and start with the mole instead, just to save some time, just to economize on time. So I'm going to start my fence post with 0.0119 moles of NaHCO3, and I'm going to convert that to grams of CO2. All right. This is a unit I can work with. I like the mole, because what it allows me to do is go ahead and use the mole ratio to stop describing this substance, this ingredient in the recipe, and start describing a product of the recipe. All right, so what I'm going to put in here is the mole ratio. The unit that goes in the denominator is mole of NaHCO3. What goes in the numerator? Mole of CO2, because that's what I want to convert to, is CO2. All right? So mole of NaHCO3 cancels out. Now, what is the relationship between CO2 and NaHCO3 according to the chemical equation? What does the recipe tell me? I make 3 CO2s for every 3 NaHCO3s that I provide, right? So my mole ratio here is 3/3. Did I want to leave the unit in moles? The question was specifically asking for what unit? Grams. So how do I go from moles of CO2 to grams of CO2? You need one more piece of the fence post. The denominator would have a unit of mole of CO2 so that these units cancel out. And then you would have grams of CO2 in the numerator. How does the mole of CO2 relate to the gram of CO2? What do I use to figure that relationship out? You use the molar mass off the periodic table. So 1 mole of CO2 happens to have a molar mass of 44.01 grams. All right? So you should recognize now that 3 over 3 is equal to 1, right? So really all I have to do on the calculator is type in 0.0119 times 44.01. If we do that, and we round out our answer to 3 significant figures, the answer should be 0.524 grams of CO2. All right, so that's how much carbon dioxide I make. Okay, part C. Part C is asking how much excess is left over. All right, well, let's take a look here. How much did I use up? That's the first thing that I need to figure out. So how much ER did I use? Did I consume? That's the first thing that's the first question you have to answer. All right. And in order to answer that question, remember I told you the other day, if you have one given, you do one fence post? Yeah, well, if you have got 2 givens, guess how many fence posts you're going to have to do? 2. The first fence post is used to figure out how much product you make. The second fence post is used to figure out this business of how much excess is left over. So you're going to have to do a second fence post here. Every fence post has to start with the given for the limiting reactant. Okay? So what we're going to do in this particular case is we're going to start with 0.0119 moles of NaHCO3. And so that's the given for the LR. And I'm going to take it and I'm going to solve it for grams of the ER. Okay? So I'm going to solve it for grams of the citric acid, H3C6H5O7. All right? When I do this fence post, the information that I'm going to get out of this is basically how much of this stuff I used up. So this is how many grams was consumed. All right? Okay, so again, it's the same relative setup. I'm starting with moles, so what I do next is the mole ratio. The mole ratio here is going to have mole of NaHCO3 in the denominator, mole of citric acid in the numerator. According to the balanced chemical equation, which is off screen, there's 1 mole of citric acid for every 3 moles of sodium bicarbonate. And those are just the numbers that come straight off the coefficients. And then in the final step, I got to change that back to grams. 1 mole of H3C6H5O7. These are ridiculous formulas, right? Weighs 192.14 grams. And so then all I do is 0.0119 times 192.14 divided by 3. And the answer here is 0.762 grams. So that's how much you actually used up. All right. They're not asking you how much was used up, though. They're asking you how much is left over. So you have to do another step here. And that final step here is you take the amount that you were given 1 gram, and subtract from it the amount that you consumed, which is what we just calculated in that fence post, 0.762 grams. And the difference here is and I really should be to 2 decimal places, 0.24 grams of citric acid is in excess, i.e. left over. Okay? And so that's how you solve that last part. Okay? It's not difficult. I will tell you what students normally forget. They remember to do this fence post and they can tell me how much is consumed. They always forget to do this part. They always forget to go back and subtract that number that comes off the fence post from the given and tell me how much is in excess. Try not to be that student. All right. '77. Any questions on 73? No? Did you see what happened? What was the problem with yours, Rachel?
I was trying to show that I didn't do the fence post. I did the original, or like the empirical value for the H1 and I subtracted
So you were doing it for moles. Is that what it was? You could do it that way. You just have to remember to change back to grams before you do that. Okay. You were doing what I was doing in the fence post. You just weren't doing in the same format. Okay. All right. Anyone else? What part of that question was giving you the most trouble? A, B, or C? Figuring out the limiting reactant, or was it figuring out the product, or was it figuring out the excess? Who wants to volunteer that information? No one wants to fess up? All right. Okay, it's all right if you don't get it. It takes a while to get this. All right, 77. When benzene reacts with bromine, bromobenzene is obtained. So here's the equation. C6H6 plus Br2 yields C6H5Br plus HBr. What is the theoretical yield of bromobenzene in this reaction when 30 grams of benzene reacts with 65 grams of bromine? And then B, they ask, if the actual yield of bromobenzene is 42.3 grams, what's the percent yield? All right, so whenever you calculate the grams of product from a fence post, essentially what you calculate is that theoretical yield. So in theory, how much of this stuff should we make based on these amounts? You have two givens. That's the number one indicator that this is what kind of a problem. It's a limiting reactant problem. So the first thing you have to identify is who the limiting reactant is, because you can't do any calculations without knowing that piece of information first. That's critical. All right, so are these units that I like to start with? Yes or no? Do I like grams? No, absolutely not. I'd rather see them in moles. So what do I need to do to change these to moles? Divide by the molar mass off the periodic table. So the molar mass for benzene, if you take 6 times the mass of carbon plus 6 times the mass of hydrogen, sums up to be 78.12 grams. And then if we do the molar mass for bromine off the periodic table, it's 159.8 grams. All right, so this reduces to 0.384 moles. This reduces to 0.407 moles. Step 1, write down your theoretical mole ratio. According to the balanced chemical equation, and in first period it was cute, I had someone ask, is that balanced? And I stopped and I said, I don't know, is it balanced? And she goes, oh, I didn't ask that. I said, oh yeah, you did, I heard you. Because she caught herself and she realized that, yeah, it was balanced. But don't assume that the equations that they give you in the book are balanced. You should always take a second to look at them and make sure that in fact you are convinced that you have the same number of atoms on both sides before you begin. Because some textbooks are notorious for giving you unbalanced equations. All right? So don't assume it's going to be provided for you. I'm going to be nice and do it for you on the test. But you should always take a second and double check your equations. And I'm happy that she did that. All right, so anyways, the theoretical mole ratio tells you that you need 1 mole of benzene for every 1 mole of bromine. So that reduces to 1, right? Let's see, they really give me 1 to 1? Well, they gave me 0.384 moles of benzene and 0.407 moles of bromine. And by the way, I'm not going to waste my time punching that into the calculator in any way, shape, or form. Okay? Because it doesn't really matter what this ratio reduces down to. The only thing that matters is that I can tell that it's less than the theoretical. Right? You know this is about 1/4 or 3/4, right? So 3/4 is less than 1. This is the empirical. So what can I tell? So it's definitely less than 1, which is what I was hoping to get. So what does that tell me? Who's the limiting reactant? The numerator or the denominator? The numerator is the limiting reactant. So C6H6 is the limiting reactant, this guy. So I'm going to come over here, I'm going to label it. I'm going to label the other guy excess reactant just because, you know, I have a tough time. I'm very visual. I have to label stuff to keep things in check and keep track of stuff. especially when, you know, a calculation takes up like an entire sheet of paper. Okay? All right, so next part. Now I can go through and calculate how many grams of this product I make. All right, well, so to do that, I'm going to start with the value for the limiting reactant. So I'm going to start 0.384 moles C6H6, and I'm going to take that and convert it to grams of C6H5Br. All right, because I'm already starting in moles, I can go ahead and jump into the mole ratio. The mole ratio will have moles of C6H6 in the denominator, moles of C6H5Br in the numerator. Luckily, it happens to be 1 to 1, according to the balanced chemical equation. Doesn't change my value very much, but I do this as a formality so that I can see how to change from one unit to the next. Okay? All right, at this point I'm not done because I didn't really want moles, I wanted grams instead. So as a final step, I'm going to go from moles of C6H5Br and I'm going to convert it to grams of C6H5Br, and the way that I do that is by multiplying by the molar mass of that particular substance, and I get that information from the periodic table. It's 157.01 grams. All right. So then all I do with my calculator is I do 0.384 times 157.01. The answer that I get at this point is 60.3 grams of C6H5Br. Okay. So that's the answer for B. So, or actually for A. For B, now what they're telling me is that, okay, so what we basically determined is that in theory, we should be making 60.3 grams of this stuff, right? But then in part B, they told me, well, we're not making that. We're falling short. What we actually made was 42.3 grams. So let's evaluate the efficiency of our process. All right, and the way that we do that is by calculating a percent yield. Percent yield is a very simple formula. Do you remember what it is? What is it? It's actual yield over your theoretical yield times 100. All right, so the actual yield has to be given to you in the question, right? The theoretical yield comes from that fence post, what we just calculated in part A. All right, so what were they giving me in the question? 42.3 grams. What did we calculate in the fence post? 60.3 grams. We take that and multiply by 100, and I get that the percent yield is about 70%. Okay, is that an efficient process? As far as chemical reactions go, it's not too bad. 70% is pretty good. There aren't a ton of reactions that go to 100% completion. Not industrial processes anyways. Okay, so if you're between 70 and 100%, we're doing pretty well. If you were getting a 7% yield, that's a big red flag that says, nah, you're really not doing well with this. Okay, time to reevaluate how you make this stuff. Okay. Questions here? Yes, no? All right, let's take a look at question number 79, the last one. Tells me that you have this hydrogen sulfide. It's an impurity in natural gas. It has to be removed. One common removal method is called the Claus process, which relies on the following reaction. It says 8H2S plus 4O2 yields S8 plus 8H2O. Under optimal conditions, the Claus process gives a 98% yield. So the percent yield is 98% of sulfur. Okay, so we get 98% of the sulfur that we should be getting out of it. That's pretty efficient, right? It says if you started with 30 grams of H2S and 50 grams of O2, how many grams of S8 would you actually produce, assuming a 98% yield? All right. So let's start with this information that we have. So they're giving me a percent yield, right? And we said that the percent yield is the actual over the theoretical. So what the question's asking is what's my actual yield? I can figure out the theoretical yield based on this, right? What they really want to know is what is the actual yield from this specific experiment. All right. I have what the percentage should be. I have that value. I can substitute it into this fraction. I can figure that out, right? Can't I figure out the theoretical yield? I can figure it out from fence posts. If I can figure out a value to substitute in here and a value to substitute in there, then it leaves me just one variable to solve for algebraically. And that's basically what we're going after. All right. So that means that I got to take some time and figure out what the theoretical yield should be. But for me to figure out the theoretical yield, again, I got a problem here. It's a limiting reactant question. I first have to figure out who's limiting. Once I figure out who's limiting, then I can go through and figure out how much of that S8 I should, in theory, make. All right. So it's tedious because they didn't give me these values in moles. They gave them to me in grams, so I got to change these to moles first. So here the molar mass of H2S is 34.09 grams. And by the way, I need you guys to check the numbers for me because I was slightly off in first period when I did this with my numbers. So I don't know. Usually when I'm off with numbers, the number one thing that I look at is molar masses. Because usually if you're off, it's you did a molar mass incorrectly somewhere. Are these molar masses right? Anyone? So far? Okay. All right, so H2S, that's 0.880 moles. And then over here for the oxygen, 50 divided by 32 is 1.56 moles. Okay, so in theory, I need 8 moles of H2S for every 4 moles of O2, right? 8 over 4 reduces down to what? 2. Okay, empirically, what were you actually given? I was given 0.880 moles of H2S and 1.56 moles of O2. So I wasn't given twice as much of the top as the bottom, did I? Again, I don't necessarily have to calculate what that reduces down to. It's pretty obvious to see that that's more like a half, right? Is a half bigger than 2 or less than 2? Okay, it's less than, right? So this is less than 2. If the empirical ratio is less than the theoretical, who's at fault? The numerator. What did I put in the numerator? H2S. That's my limiting reactant. This is my excess reactant. Okay. All right, so if I want to figure out how many grams in theory of S8 I should make, I should start my calculation with that value. All right, so we're going to do that. 0.880 moles of H2S. I'm going to change that to grams of S8. There are 8 moles of H2S for every 1 mole of S8 produced. And I don't need that value in moles, I need it in grams. 1 mole of S8, let's see, 32.07 times 8 weighs 256.56 grams. So I calculate that I should be making 28.2 grams of S8. All right? Okay, so now if my percent yield is 98%, and that's equal to my actual over my theoretical, which I now know is 28.2, right? So I'm going to substitute this in for this bottom number times 100, right? Now I can solve for actual. So what's the first thing that I'm going to do here? I'm going to do 98 divided by 100, right? Or 0.98 is equal to my actual over 28.2. So I'm going to multiply by 28.2. And I'm going to get that the actual yield was 27.6 grams of S8. Okay. And so that's basically how you do that. Questions? Yes? No? All right. So I would say that a good portion of the quiz on